Okay, if you remember in the last few classes we talked about flying and handling qualities of aircraft. And these qualities were based upon which class of aircraft, which category of flight, and the levels, and all of them were related to where the eigenvalues of the aircraft dynamic modes are located in the complex plane. So, this is how typically we saw the eigenvalues of aircraft located in the complex plane, right. So, clearly the real eigenvalues are giving the time constants, and the complex conjugate eigenvalues are giving us the damping and the frequency characteristics. Now, the question is let us say our basic aircraft design results in giving us in one of the flying conditions, not all, but let us say it results in giving us the eigenvalues at these places located in the complex plane, right. And let us also assume that these are not what is required according to the flying and handling qualities. So, remember we said that flying and handling qualities will depend upon these parameters associated with the location of the eigenvalues of the aircraft in the complex plane. So, if there is no matching of what is required and what we have achieved by the design, then either we can find out the parameter, the aircraft design parameter, which can be changed so that we get the location of the eigenvalues in the complex plane as required by the flying and handling qualities, or we do something else, and that something else is related to the subject of aircraft control. So, what we are looking for is we are looking for artificially changing the dynamic response of aircraft small perturbation motion, and also when we are trying to execute maneuvers, there also we want the aircraft to follow certain desired dynamic behavior, which can be achieved by the aircraft control systems. Typically, the task of aircraft control system will fall in three different categories. One is stability augmentation. So, control system which results in providing artificial stability to the aircraft are known as stability augmentation systems, and in short form it is also written as SAS. Okay. The other type of control task is to augment the control system itself, and those control systems are called control augmentation systems. So, task of this control system can be, for example, commanding the pitch rate, or commanding the, for example, the acceleration. There are other class of control systems which are designed for pilot free flight, wherein pilot does not have to do any work. He just fixes some number or attitude of the aircraft, and he can leave his hands off the control surfaces or sticks, and automatic control systems take care of the desired dynamic behavior of aircraft. So, in this category we have control systems. Okay. Autopilot control systems are those control systems where pilot can fix the desired attitude and the path for the aircraft and leaves his hands off, and the control system takes care of the aircraft. So, in this class we will first look at the stability augmentation system. So, as the name suggests, this particular type of control systems is for augmenting the stability of aircraft. So, what essentially it does is it helps in locating the eigenvalues suitably using a feedback mechanism. So, let us go back to our equations of motion, where we had the complete aircraft equations of motion written in compact form as linear control systems are actually designed around particular equilibrium flying conditions, and those flying conditions are obtained by setting this derivative of the aircraft state variables to 0, and so we have equilibrium conditions which are denoted by x star u star. The linear model around the equilibrium point is developed using small perturbation theory, and what it gives is now this matrix is a matrix of constant numbers at this equilibrium flying condition, and that we called as system matrix A, and this matrix is also evaluated at this equilibrium point and is called the control matrix. So, A is system matrix and B is control matrix. So, we have our linear aircraft models around equilibrium point. Aircraft response in perturbed variables are governed by the eigenvalues of the matrix A, which we obtain by solving this equation of characteristics, and these eigenvalues are located in some fashion in the complex plane. What we essentially want is, we want to move these eigenvalues in the complex plane, so that we can finally achieve what is desired for the aircraft by the flying and handling qualities in terms of time constant or the damping ratio and frequency characteristics. Okay. So, and that of course has to be done through this delta u. So, there is one case when this delta u is 0. So, aircraft is at some equilibrium condition, is flying, and whenever small disturbance is hitting the aircraft is showing some response, okay, and that can be stable yet not so desired. So, zeta and omega n, for example, may not be what we want. So, one of the response, let us say in some variable x1 or the perturbed variable is looking something like this. This is the natural response. What we are intending to do through the stability augmentation system is to modify this response as desired. There are many ways of doing that. Linear control theory or classical control theory is full of techniques which help you to define this delta u in some fashion, as for example this. So, here this delta u is modified according to the change in state variables, perturbed variable, using this constant k, this k is called gain, and it can be a matrix, because we want to control response of aircraft in different variables, then this matrix, this k is not just one gain, but a matrix of gains or a vector of gains. Let us see what it does to this linear model. When we incorporate this delta u in the model, linear model, it changes the system matrix through the control input. So, the new system matrix, when we talk about including this law in the linear model, the new system matrix for this model becomes A minus B into K. And now, if we want to look at the behavior of aircraft, including this control system, then we have to solve the eigenvalues of this equation. So, clearly a inclusion of this matrix or the vector of gains k modifies the eigenvalues, or when you change the gains, moves the eigenvalues to a location which is desired, and that value of the vector gains can be used to design the feedback control laws. Let us look at one example here. So, we talked about constrained yaw motion of aircraft in one of the lectures. About an equilibrium condition, and the equation, linear equations for that particular case. So, aircraft had only one degree of freedom, that was in yaw, and the equation of motion in the perturbed variables around the equilibrium state turned out to be this. What we could find from here was the natural response of the aircraft to disturbance, and that was by solving a quadratic equation corresponding to this equation Of course, if we do not change this delta r, delta r from the steady condition, then what we are looking at is the response, free response, and that is given by the solution of this set to 0, and then it becomes an eigenvalue problem. So, the eigenvalue problem corresponding to this system when delta r is 0 is will result in giving us the damping ratio and the frequency, which is square root of n beta, and the damping ratio is this. What we want to do in this case is we want to design a stability augmentation system which will enhance the damping of aircraft in yaw motion, and that will also have an effect on the frequency. Okay. So, let us see if what happens if we change the rudder deflection around the fixed equilibrium condition. So, this delta r now can be deflected around the trimmed condition according to the feedback. So, what it does, it reads the delta psi from the equilibrium condition, multiply it by this factor k. So, this factor k is actually sitting as controller. So, it reads this delta psi, multiplies it by this factor k, and deflects the rudder according to this formula. So, what this does is to the equation is okay. So, what we achieve by deflecting the rudder in such a fashion is changing the stiffness coefficient to n beta plus k into n delta r. So, what it's going to do is it's only going to change the frequency of the natural frequency of the response. In case we also want to change the damping ratio, what we can do is through this feedback mechanism, if we not only read the change in the yaw angle from the reference condition, but also if we can modify delta r based on the rates, then we can achieve a change in not only the frequency characteristics, but also the damping characteristic. So, this is how it happens. So, let us look at how is changing the frequency and damping both together. So, now the new damping ratio, the expression for new damping ratio and the frequency are these. So, clearly clearly deflecting the rudder around the equilibrium point or around the equilibrium value of delta r corresponding to the that particular trimmed condition. If we deflect a rudder in this fashion, then we can modify the damping ratio and the frequency characteristic and the location of the eigenvalues in the complex plane, and that is done through these two gains K1 and K2, which can be adjusted. So, K1 and K2 can be adjusted to give the desired response with respect to the disturbances from the equilibrium condition. Okay, so let us look at another. This is how typically a yaw damper will work. Let us say we want to modify the short period dynamics. Right. We want to modify the short period response of aircraft using stability augmentation system. So, what we have is some response which is given by alpha over delta E. So, to input in elevator, aircraft is giving some response in angle of attack, and we want to modify this response using stability augmentation system. So, in general, if you have an open loop and the pilot is using the stick which is giving the deflection elevator, the response is angle of attack which is governed by this ratio, which is called also or system dynamics, which is alpha dynamics in this case. Okay. So, pilot is giving a stick command and there is some response in angle of attack, and that response will depend upon the aircraft parameters. What to be achieved by stability augmentation system is artificially adding to the artificially changing the dynamic response of aircraft around the normal condition. So, this is an open loop model. Now, if you want to see how a stability augmentation system will work, which is a feedback system, so this is delta E, which is given by the pilot, and because of this feedback loop, the stability augmentation system results in changing this pilot input by this amount. So, what delta E we see is now delta E, which is sum of delta E coming through the stability augmentation system and the pilot input, and in this case this delta E SAS is k into alpha. Okay, let us look at what is happening here. So, we have the equations for the pitch rate dynamics, which is given by, so this is again a constrained situation. So, this delta E here is delta E pilot plus delta E stability augmentation system, and which is also delta E pilot minus k alpha. So, what it does is it modifies this is right. Delta is okay. So, now because of this stability augmentation system in place, this quantity which is representing the frequency of the short period motion is automatically modified, and so therefore, it has an effect upon on the dynamic response and the stability characteristic of the aircraft in short period motion. In general, a typical stability augmentation system will not look so simple, but it will be involving a lot of other elements. So, to give you a very brief introduction to the technique which is used to design stability augmentation system, using one of the techniques called Laplace transform technique, which is applicable for linear system models as shown there, which is so clearly if we want to transform this equations in algebraic form, we can use Laplace transform technique, and it results in giving us the relation between the input and output, which is in this case we know that the open loop response is governed by the solution of determinant of Si minus A equal to 0, and this function which relates the input and the output is called as transfer function. So, this alpha over delta E in this case is the transfer function for the open loop model, and the response is governed by the solution of this in S. S is also similar to eigenvalues, is here called characteristic values. Now, let us see what happens when we close the. So, Gs is the open loop transfer function, and the response is okay. So, there is some response, the output corresponding to this input R s. So, in our case is x and u. Now, the usual notation is to use C and S for the output and input respectively. So, what happens when we close the loop is it changes the input characteristics depending upon the error that is fed back through a feedback element. New input output relation with this feedback system in place is this, and this is closed loop. Transfer function. When this happens, clearly the denominator here is modified, and this is solution of this is what governs the dynamics. So, now if we want to look at the behavior, that will be governed by the solution of this equation, which is the characteristic equation, and the solution of which is S, and S is also nothing but the poles or the eigenvalues of the closed loop, poles and eigenvalues of the system.